Well, my body's adjusting to getting up early, so got a reasonable sleep last night, so I should be more awake this time. Now we are in the middle of a rather difficult proof. We're trying to show that a grammar, context-free grammar, and an automaton, a stacked automaton, a PDA, a push-down automaton, that there's an equivalence between the two. So if you have one, you can design the other that does the same thing. Okay? So doing the same thing in this context means that they both describe the same language. They have equal power, in other words. And this equivalence proof, the theorem statement, was two-part, was an if and only if. One way, in one direction, the statement was that if you had a given PDA that could recognize a given language, then you could build an equivalent grammar, a context-free grammar, that would generate the same language, in that sense of equivalence. And we proved that. And now in the process of proving in the other direction, going the other way, so you start with a grammar, context-free grammar, CFG, and you want to prove that it can, that the language that it generates, because it's a grammar, right? Grammars generate languages. They generate the strings of the language. And all the strings that the grammar can generate, they are the language. You know, they're the members of the language. And the second part of the proof is saying that you can construct a I'm trying to remember which way we go. You can construct a grammar that behaves like a PDA, right? So in the first part, we were constructing a PDA that behaved like a grammar by using the stack. You're putting the intermediate strings on the stack. And this time, we're going the other way. We're trying to construct a grammar that behaves like a PDA. So whatever the PDA can do, and what do PDAs do? Well, they recognize strings. So we have to create a grammar that behaves like a PDA. So to do that, we need to have a clear idea of what's going on with the PDA. What does the PDA do that the grammar has to mimic, so to speak, so that whatever string the PDA can recognize, the grammar can generate, right? So PDAs recognize a string. In other words, they go through a series of states. You know, they read the input string, a symbol at a time, and after reading each symbol, the automaton will transition to some other state, usually. And eventually, once it's finished reading the input string, it'll be in a state that is an accept state if that string belongs to the language that the PDA is recognizing. Now, if it terminates in a state that is not a member of the set of accept states, then that string is rejected. That string does not belong to the language that the PDA recognizes. Okay, so the PDA is going, it reads in a symbol from the input string, it'll change its state. Okay, so if it reads in, let's say, a substring, so let's say a middle portion of the input string, and at the beginning, you know, when it reads in the first symbol of that inner portion, substring, let's say it's in state P, little p, and it reads, you know, it reads the subset, the substring, and it's now read the last symbol of that substring, and now it's in state Q. Right? So it went through a whole series of states in between P and Q in reading these symbols, these input symbols in the input string, and now it's so it's finished reading the last symbol in the substring, and now it's in state Q. Okay, so if we can, and it's read the substring. We could call it X. Call that substring X. So it's just it's a sequence of input string symbols, right? Sequence, and you could call that substring X. And the PDA starts off in state P, reads the substring X, and finishes reading that substring X, and it's in state Q. Okay, that's what PDAs do. All right. Now let's try and create a grammar that behaves the same way. Okay, because we're trying to show. I mean, try to remember the big picture. What we're trying to show is that we can create a grammar that behaves in the same way as the PDA. Whatever the PDA can do, the grammar can do. Okay. Now the PDA does it in its way, a PDA way, and the grammar does it in its way, a grammar way. And the PDA way of doing things is reading in input strings and switching from state to state. Right? That's the PDA way of living. And the grammar, what's it doing? Well, it's using substitution rules and substituting a variable for, well, usually a string of, it's usually a mix of terminals and variables. Okay, so it keeps substituting until eventually there are no more variables left in the partial, the intermediate string to be substituted. You end up with just the string is now just all terminals, and that's the end of it. So that string of terminals, the grammar has generated. Okay. And so a grammar describes a language. It's just the set of all strings that the grammar can generate. Okay. All right. So how to link these two? So if any string that can be recognized by the PDA, an equivalent grammar would generate. Okay. Generate the same string. So. So if the whole string goes into the PDA, then the grammar would generate that whole string. Now, if we have the substring like X, the PDA, that substring goes in, and we would want the grammar then to generate that substring X. Okay, and if it can do that for no matter how big or small X is, if it's always generating the same substring X, then those two machines, those two things are equivalent, right? Because they're doing the same job. Okay, one's recognizing a string, and the other one's generating the string, but it's the same string. It's X. Okay, so that's the sort of the main idea. Now I hope think about it. This proof is quite complex. It goes over several boards. This is our second board on this part. It only finishes second half of the fourth session, right? So we've got there's eight squares on a board, so we've done 7 of the 8 squares on this board to come. So a long proof. The proof has parts, the parts have parts, and even the parts of parts have parts, right? So it's long in that sense, and fairly complicated. So you will really need to give this one some thought. Well, and it depends how smart you are. I mean, if you're really smart, it may be fairly obvious to you, and you just take it in your stride, and not a problem. If you're struggling a bit, you will need to give it some effort and some thought. And for some of you, maybe it's just too much. I do remember when I was lecturing this topic, theory of computation in China. I think I've mentioned this once or twice. My Chinese dean insisted that I open up this master's level course, as I planned it originally, to seniors, undergrads as well. And I said, oh, I don't know if that's wise. You'll have a dropout rate. It's hard. And he insisted, and a third of the undergrads did drop out. It was just too hard for them. And this kind of proof, this level of abstraction and so on, is an example of the kind of thing that caused them to drop out. So it's not trivial. All right. Okay. Okay. So with that, I was trying to give you an overview, like a feel for the thinking that's underneath, between the lines, so to speak, of the proof. So hopefully that helps. So let X be your substring, and remember that we're trying to create a grammar. We're working on the grammar, right? The PDA is given. It's recognizing a certain language. In other words, all the strings in that language. So the PDA is given. So we're trying to find the grammar. So we need to find its formal definition. So we need to know all its variables, right? Because that will be what's substituted for, and we'll need to find its rules. So we have to construct the grammar. We have to build the grammar, and do it in such a way that that grammar behaves in just the same way as the PDA. In other words, the grammar generates a string, the PDA recognizes the string. If the PDA if it's read a substring and it started off in state P, reading the substring, and it ends up in state Q, having read the substring, then the grammar that we're generating will generate the same substring, X, call it X, that the PDA has